Okay, here's an investigation paper on the spread of a virus. I think it's from 2017. Virus. You are advised to spend no more than 45 minutes on this part. This investigation looks at the way a virus spreads in plants in a field. Number one, in a field, there are a large number of plants in a straight line. The diagram shows the plants near the middle of the field. So each dot here represents a plant, and it's said that they are in a straight line, so just one line of plants. On day one of the plants is infected with a virus. So we can see you've got a plant with a virus denoted by the V, and then around it you've got all these healthy plants that are not yet infected. Day two. On day two, that plant is dead. So this plant that had the virus is now dead, and that's been marked with a D, and the virus infects the plants that were next to it. So these two healthy plants, well, they were healthy yesterday, and this had the virus, and then one day later, the one that had the virus is dead, and the two healthy that were next to it have contracted the virus. That's day two. This continues from day to day, so this is the pattern on day three. So on day three, you've got 3 dead plants and 2 plants with the virus, and then lots of healthy plants along the line. Don't think that this line stops, it keeps going and going. Right, so you have the plant that was dead yesterday is still dead. The 2 that had the virus yesterday are now dead. And the 2 healthy ones that were next to plants with viruses now have the virus. The diagram shows that the virus infects 2 more plants on day 3. So the total number of plants that are infected or dead is 5. Complete this table. Right. So just looking at, I mean, you can draw a little sketch if you like, but each day you just get 2 more. This is only looking for the number that are infected or dead. So every day 2 more are infected. The next day these 2 will have the virus and these will be dead, but they're classed as infected or dead. So every time it's +2, +2, +2, +2. So on day 4 you're going to have 7 plants infected or dead, and day 5 you will have 9 plants that are infected or dead. Right, find a formula for T in terms of n. So now we're into sequences already. So what I'm going to do, and this is for a communication reason as well, I'm just going to write the sequence out. 1, 3, 5, 7, 9. 1, 3, 5, 7, 9. And looking at that, this has a constant first difference. This is an arithmetic sequence. +2, +2, +2, +2, +2, +2. And there are, if I show you the communication marks, if I were to show you those, you would see you get communication marks for showing that you are recognizing differences. Now, you've got 2 options. You should really, this is a linear sequence, an arithmetic sequence, as in it increases by a constant amount each time. You should really be able to find the nth term of this without a calculator. That the +2 means 2n, and then the other bit, it's basically if n was 0, what would this be? So I've unfortunately got this page number here, but what would this number be that you add 2 to in order to get 1? Well, you could either just take away 2 from 1, which would get you -1, or you could think, well, what would that number be? And it would still be -1. So the nth term is 2n minus 1. Now, if you're not confident with that, as long as you've recognized it's a linear sequence, don't forget your calculator will do this for you. If I go to menu and statistics, and I just put in the ends, as in the term number in list 1, so how many are there? 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, and then just put the actual term, which is 1, 3, 5, 7, 9. If I just do that, and then I go to calc and reg for regression, and I know it's linear, that's the x regression, and it's ax plus b, and it tells me if it's ax plus b, it's 2x minus 1. Well, we didn't have an x, we had an n, so it's still 2n minus 1. But it does say find a formula for t, so I would probably get the mark for that, but if it wants it in terms of t, I'm going to write t equals. Right. On which day are there a total of 97 plants that are infected or dead? So really that's saying, when does 2n minus 1 equal 97? Do write that down. However you go on to solve this, you should write that down. And it's a really friendly linear equation. You're going to add 1 to both sides, so 2n equals 98, and then you're going to divide by 2. n equals 98 over 2, which is 49. So it's day 49. If you can't solve that, then you could potentially use a solver or draw a graph or something like that. But I'm going to assume that you can all solve a linear equation like that. I very much hope so. Right, in another field, there are a large number of plants in equally spaced rows and columns. The diagram shows the plants near the middle of the field. So here you go. You've got this. On day one of the plants infected with a virus. There it is. And then you've got a lot of plants next to it, and it infects lots. So if we just look at day 1, you have got a plant with a virus and lots of healthy plants around it. The difference between this and question 1 is that before it was a line, and now you've got the virus spreading in 2 dimensions, right? So these investigations and the modeling sections, they start off really, really simple. And then they change a bit, they twist it a bit, and then the algebra gets heavier, the more constraints come in, something like that. This is the pattern they follow. They start off really nice, and then something changes, and then something else changes. Right, so on day 2, that plant is dead, so this one here is dead, and the plants next to it are infected. So virus, 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 and that was yesterday's virus plant, now dead. Day 3, all of the plants that had the virus yesterday were dead. The plant that was dead yesterday is still dead, so the middle one's dead, and then you've got dead, 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 and then you've got lots of virus ones around it. You've got in total 5 dead and 8 infected plants, right? So we're seeing the pattern, it's just introducing the pattern. Now we're going to have to do something with it. Right, draw the pattern for day 4. Right, so if it was me, everybody's different. You might find your own way of drawing these things, and everybody's brain works a bit differently. But for me, it helps me to, if I can think of this middle cross. So all of these are going to be dead tomorrow. I'm going to have 1, 2, 3, 4, 5 Ds, and then I'm going to have 1, 2, 3, 4, 5 Ds in the middle. So if I get that middle line, I should be able to draw everything else from there. So I'm going to say dead, 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 dead. So that's my 1, 2, 3, 4, 5 middle one, and then I'm going to do the same going the other way. So I've got 5, we start in the middle, dead, dead. So that's 1, 2, 3, 4, 5. So that's everything dead in this one cross, sorry, not everything dead. And then looking at that, I now can put in everything else yesterday and see where we go from there. So we're now going to have this is dead, this is dead, this is dead, this is dead, and that completes yesterday's arrangement. So it's everything that was dead already is dead, and everything that had the virus yesterday is now dead. I could check that that's 13, because this was 5 and 8 is 13, so just a little check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Right, so I'm happy with that. Now I'm going to put my virus-ridden plants in. So remember, it only spreads sideways or down. So what it doesn't do is spread along the diagonal. So virus, 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 and virus. With these patterns, it's quite good. If you did make a mistake, if you missed one, it probably would show up. Say you just missed one, it would really look like a hole. So that is the pattern. Complete this table to show the number of infected plants each day. You may use this grid to help you. So it only wants the number of infected. So I already have day 1, 2, 3, and 3 days are in. So 1, 4, and 8. So this is the pattern for day 4. So I should be able to fill in day 4, which I'm just looking for infected. So just the V's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so I could look at this and say maybe that's going up in 4s, but I don't really have enough information to do it. It says you may use the grid to help you. You might not need the grid. It really depends how you operate. Now I'm thinking it might be easier just to use this particular grid and just think, well, I'm going to have here this many, 1, 2, 3. If I just draw these dots, I'm not going to lose my marks for the other bit. As long as I can see it, then that will tell me how many new plants will be infected tomorrow. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It will be 16 more tomorrow. If you want to draw the pattern, that is fine, but I'm finding I'm probably less likely to make a mistake with what I just did. However, it really does depend on the question. Sometimes the grid could be really handy. But if you were going to use the grid, I would do something like 1, 2, 3, 4, 5, 6, 7 Ds across here, 7 Ds along here, and go from there. Right, so now we have a table. Another thing with investigations, and this is all I say all investigations, but many, a high proportion of investigations, they start with patterns, then they go to tables, and then they go to nth terms. This happens so often, so you do need to be ready with this sort of layout. Right, what is next? Work out a formula for the number of infected plants P in terms of n for n is greater than or equal to 2. So that is interesting because if we're only interested in n is greater than or equal to 2, as in this bit here, because it doesn't really work from the first day, you add 3 here, but from then on it's plus 4, plus 4, plus 4. So that's why it does seem to be a nice pattern from day 2 onwards. So what I'm going to do, I'm going to write these numbers 4, 8, 12, 16, 4, 8, 12, 16, and remember that was for n equals, so n equals 2, n equals 3, n equals 4, n equals 5. So what you want to do is be very, very careful with using the method that I showed you here, because if you were to do something like this, as in do the differences and then look at the 0 term, it wouldn't be the 0 term right now. So because remember we started on term 2 here, this is when n is 1, 2, 3, 4, 5, 6. So if you want to do something like that, your best bet is to just sort of have a ghost term here, which would be 0. You think if n equals 1 according to the sequence, this would be 0. And then you could use that approach. You could say plus 4, plus 4. And remember, we get marks for seeing, communicating that we can see differences. Plus 4, remember the plus 4 means 4n. And then we look at the 0 term. So if this would be the first term in this sequence, ignoring what we had before, then the 0th term, when n was 0, this would be minus 4. So that could be 4n minus 4, and we're looking for p equals. And remember, this only is supposed to work when n is 2, 3, or 4. So just to show you that it works, we have 4n minus 4. So if n is 2, 4n is 8, 4n minus 4 is 4. If n is 3, 4n is 12, 4n minus 4 is 8. If n is 4, 16, 12, 5 times 4, 20, 16. So it works, which is good. Another thing you could do, if you aren't comfortable with what I just did, you can go back to the regression tool. So if I just go back in here, what you do have to do is alter your ends, because it doesn't start from 1. So I'm going to delete these, and I'm going to start from 2. So I'm going to 2, 3, 4, 5, 2, 3, 4, 5, and then I'm going to put the sequence in, which was 4, 8, 12, 16, 4, 8, 12, 16. I would do that, go back to ax plus b, and it tells me it's 4x minus 4, which is 4n minus 4. So you can use the regression tool. It's a calculator paper. It's there to be used. And you'd get your communication marks still. I would still recommend showing these differences and showing that you know it's a constant first difference. Okay, part D. Complete this table to show the total number of infected or dead plants. Right, so infected or dead. There are two ways to do this. I would suggest one is a lot more efficient. If we go to the beginning, here we had on day 1 you have just this one plant with a virus, right? So on day 1 it's 1. On day 2 you've got 1 dead and 4 with a virus, making 5 in total. On day 3 you've got 5, 1, 2, 3, 4, 5 dead, and then you've got 8 with a virus. So it tells me there, I don't know why I'm struggling. So what you can do is keep drawing patterns and counting them all. Or you can just think, if you know these numbers up to here, what happens is you only add the newly infected ones on. So if I take the different from day 2 to day 3, to get from 5 to 13, it's all the plants that were dead or infected, which was the 5, plus the newly infected. So what that is, plus these 8. So we actually have a table of the infected. So all we need to do is add on 12 and 16, because we already know what the total dead or infected is at the end of the day. Then we just add on the number of just infected. So if we add 12 and then add 16, it will get us to there. If you're not happy with that, you could draw some more diagrams and count them all. I'm not going to do that. I'm just going to do 13 plus 12, and then the answer to that plus 16. So I'm going to add 12. 13 plus 12 is 25, and then I'm going to add 16. And remember, I'm adding 16 because on day 5 there are 16 infected plants, and on day 4 there were 25 dead or infected, so I just add the number of just infected on the next day. So 25 plus 16 is 41. Find a formula for t in terms of n. So again, standard sequence approach, you write out the sequence. 1, 5, 13, 13, 25, 41. Find some differences. I mean, you could, I suppose it's good practice to just check it's not geometric, as in this is times by 5, there's times by 5 work here, it doesn't. So you could check it's Fibonacci, 5 plus 1 is 6, no, it doesn't work. So then we go to differences. So draw your arrows for your differences. Plus 4, from 5 to get to 13 is plus 8, 13 to 25 is plus 12, and 25 to 41 is plus 16. This looks promising because I think I'm going to have a constant second difference. Plus 4, plus 4, plus 4. Right, so constant second difference implies two things. Firstly, it implies it's a quadratic sequence. Quadratic sequence, which means that it's going to have an n squared in. And actually, the n squared term is always half of the second difference, so it's definitely going to have a 2n squared and then probably plus some more stuff. Now, I am not going to do this one using a non-calculator method because it's a calculator paper. I'm going to use the quadratic regression tool. It's there, it saves you time. If you want to know how to do this without a calculator, then please refer to another video. So I'm going to go back to the regression tool. I'm going to have to change my ends, remember, because this time it did start from day 1, as you can see there. So I've got 1, 2, 3, 4, 5. And the numbers are 1, 5, 13, 25, 41. Okay, so I don't want a linear regression. I know it's quadratic. I need an x squared regression, so I need this one here. X squared regression, and that tells me it's ax squared plus bx plus c. A is 2, b is minus 2, and c is 1. So it's kind of like 2x squared minus 2x plus 1. That's your ax squared plus bx plus c. But remember, we don't actually have any x's, we have n's, and we've been asked for a formula for t. A formula really means it should have an equal sign. It should tell you t equals something to do with n. So it's going to say t equals 2n squared minus 2n plus 1, just like that. Okay, show that your formula works when n equals 6. So this is a little bit frustrating because I'm sort of being invited to draw a grid, and just think, putting myself in your shoes in an exam, that's probably how you're going to do it. So I must admit I'm regretting a little bit not drawing pattern number 5, but we'll give it a go, and it should be okay, because I'm still going to look at this cross through the middle arrangement and just think about how I can use it to draw it. So if we just think logically, on day 1 you've just got this one plant with the virus. Day 2 you've got this one dead one in the middle. Day 3 you've got 1, 2, 3, 1, 2, 3 dead ones in the middle. Right, so 1, 3, on day 3. On day 4, we did draw day 4, you have 1, 2, 3, 4, 5 dead ones in the middle. So that means on day 5 you're going to have 7 dead ones in the middle, and on day 6 you're going to have 9 dead ones. So if I draw 9 and 9 on my space for dead 6, so for dead 6, day 6, that should help me quite a lot. So let's start there. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we need to draw in the middle, so you to split the 9. Well, that's going to be the 5th one. It says 4 either side. 1, 2, 3, 4, 5. And I want 9 on the other way. So 1, 2. So that's 3 total. 4, 5, 6, 7, 8, 9. So that's that initial center cross. And then I can just sort of start to put them in. So I know that this is going to be virus, 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 like that. And then I can just sort of start to fill in the viruses. So actually, well, I can fill in the dead or the viruses really. So I think the easiest way I'm going to find it, if I just look at the way these go, once you've got these kind of 4 viruses on the edges of that cross that I was talking about, from there they just kind of go on the diagonal like this. And so I'm just going to draw like this. I'm going to draw virus diagonals up to there. Virus, 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 virus. Because remember, it's only the ones on the edge that have the virus. Virus, 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 virus. Go this way. Virus, 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 virus. Go down. Virus, 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 like that. And then I've just got all these dead ones in between. So dead, 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 dead. Right, so that is the pattern for n equals 6. So I need to show that my formula works. So the formula is t equals 2n squared minus 2n plus 1. So when n equals 6, t, as in, remember what t is? It is the total number of infected or dead plants. Right, so it should be 2 times 6 squared minus 2 times 6 plus 1. So if we go to our calculator, in the main bit of the calculator, the run matrix, 2 times 6 squared minus 2 times 6 plus 1, so that gives me 61. So I need to probably find a way of counting these. I've drawn it anyway, but let's just count. So we know we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 there. And then if I kind of draw this bit, I've got 2 sort of symmetrical equal sized triangles there. So if I can count these, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So I've got 25 and I've got this must also be 25. So that would mean from the diagram 25 plus 25 plus 11, 25 plus 25, 50 plus 11 equals 61. So I think that's probably enough to show that it works when n equals 6. On which day are exactly 2 plants infected? On which day are exactly 221 plants infected or dead? So it's similar to the other one we did, it's just more complicated, the equation. So you're looking to find when does 2n squared minus 2n plus 1 equal 221. So this is a quadratic equation. I would imagine it'll be quite a nice friendly one that factorizes, but it is a calculator paper. You could potentially use a solver. I'll show you how to do a non-calculator method, which would mean you would subtract to the 221. You want it to equal 0. So 2n squared minus 2n. So 1 minus 221 is minus 220 equals 0. You have a 2 in all of these. So given that we're only looking to find the number, you could divide through by 2. So you could say, well, n squared minus n minus 110 equals 0. You could try and factorize that, and 110 is 11 times 10, which probably will work. So n, 11 and 10, if they had different signs, the 11 would have to be the negative 1, because we add to make minus n, and the 10 would have to be the positive. So n would equal 11, or n equals minus 10. Using the null factor law, remember, this times this equals 0. So either the first bracket equals 0, so either n minus 11 equals 0, meaning n equals 11, or n plus 10 equals 0, meaning n equals minus 10. This is impossible. How can n be minus 10? So the answer is day 11. Now, if you're not very good or very confident with quadratic factorizing, or even if you just think it's going to take you a long time, you could draw two graphs. You could draw a graph of 2x squared minus 2x plus 1, and you could draw a graph of y equals 221. You could find an intersection, or you could go to the solver as an equation, and you can go to polynomial. Degree is 2 because it's a quadratic, and you can just type in. I would actually have to make it equal 0 before I did that, so that's kind of the disadvantage of using a solver. You would have to do a little bit of algebra. So I would put in 2 x squared minus 2x minus 220 equals 0. So I might solve like that. Press solve, and you still get 11 and minus 10 as your answers. I won't show you the graphical method, but literally you would plot the left hand side, plot the right hand side, adjust your window so you can see the intersection or intersections. There's 2, and then just solve. Probably if you're doing it that way, draw it, but I don't think for this particular one, I'm not certain, but I don't think you get a communication mark for that. But you don't need to show communication in every question, just enough of the questions to get the communication mark. Right, what's next? Number 3, in another field, on day 1, 8 plants in the arrangement below are infected. So this is a slightly different arrangement. You've got 1, 2, 3, 4, 5, 6, and you've got a bit of a gap, healthy plant there, and then 2 more that are infected. On day 2, these plants are dead, and the plants next to them are infected, so the virus is still spreading in the same way. Show that the number of plants that are infected on day n, as just infected, as in the V's, where n is greater than or equal to 2, is 4n plus 3. So I've got some grid. I've been asked for a show that. I'm going to have to draw some diagrams. So this is day 1. Let's draw, if we just sort of draw maybe day 2, day 3, day 4. So day 2, you're going to have 1, 2, 3, 4, 5, 6, all of those that will be dead. So we'll have dead, 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 and then you've got the virus runs around it. So virus, 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 virus. Right, so that is day 2, and we're interested in the number that are infected, and it's to show that. I'm just going to write it down. So just the number that are infected: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's 11 with the virus. So on day 3, you're going to have, so all of these will be dead. I'm going to need a bit more room, so I'm going to go down 1. So I'm going to have 1, 2, 3, 4, 5 dead, like that. Give yourself room for a virus 1 at the top. 1, 2, 3, 4, 5, like that. 1, 2, 3, 4, 5. Another 5 dead. 1, 2, 3, 4, 5. 1, 2, 3, 4 dead from here. 1, 2, 3, 4. 2 dead ones there. They were up. 1 dead, dead. And just these 3 on the side, actually. Dead, dead, dead. Right, so they are all the dead plants on day 3. Just need to spread the virus around. So virus, 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 virus. It's just the amount with the virus. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, we'll draw day 4, and I'm not going to have room for day 5 anyway, so once you've drawn 3 more patterns, you really hopefully will see something emerging. So number 4. So I'm going to have 1, 2, 3, 4, 5, 6, 7 dead. Leave myself room for 1 more as well. 1, 2, 3, 4, 5, 6, 7 dead. That's that row, and then another 7 dead next to it. 2, 3, 4, 5. Okay, so that's these. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 dead like that. So 1, 2, 3, 4, 5, 6. That was that. 1, 2, 3, 4 must be there. 1, 2, 3, and 4, and then just 1, 2 here. On the other side, 1, 2, 3, 4, 5 must be here. 1, 2, 3, 4, 5, and 1, 2, 3. Like that. Spread the virus around. Virus, 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 virus. Right, count the virus and make sure you know where you started from. So I'm going to put a little dot there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I counted that 19, so I'm pleased about that, because now I'm going to assume that this is going to continue going up in 4s, right? So I'm going to say n. So when n is 2, 3, 4, t, not t, so this can be v. It was P actually, wasn't it, before, but never mind. It's not offered as a letter this time. Let's say V for not just the number of V's. It is 11, 15, 19. So I'm going to assume that that's going to be 23. And if you're not sure about that, you could always just count some dots. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on. There will be 23. So when n is 5, it's going to be 23. All right, so that's the table. Constant second difference, plus 4, plus 4, plus 4, which means 4n. And then remember, well, what you could do, you could say, well, what's 4 times 12? Sorry, 4 times 2 is 8, and then I need to add on another 3. 4 times 2 is 12, I need to add on another 3. So that's looking like 4n plus 3, or you could sort of go backwards. So if I had my sequence that was 11, 15, 19, 23, if n started at 1, assuming that this wasn't the pattern for 1, it actually followed the sequence all the time. So it would be 7, and then so if n was 0, it would be 3. Either way, it's 4n plus 3. If you can't do any of that, you could use the regression tool, but you're probably not going to meet to show that. But I think having the diagrams, we're showing this works, we've shown the difference, I think that's probably enough. Find the expression for the total number infected or dead on day n. Right, so I'm going to draw a table, n, and I'm going to use t for total number. And I'm definitely not going to draw any diagrams. We're just going to use sort of a combination of the information we have and the methods that we've used before. So if you remember, when we filled in this table before, with the total number of infected or dead, we have these little, this plus 12 plus 16. Remember, that was the amount of newly infected plants on the next day. So we have the number of newly infected plants that we were calling P. I've just started calling them V, but it doesn't really matter. So all we need to do is get the total from one day and then just add on the newly infected, and that will give us a total. So if we then, and this is from n equals 2 again, so we're going to start from 2. N is 2 or greater than 2. So when n is 2, the total number, well, it's the 11 infected plus 1, 2, 3, 4, 5, 6, 7, 8. It's 19, right? And now from there, we can just add on these numbers. So we know after day 2, so for day 3, you've got 15 newly infected plants. So you just do 19 plus 15. Like that, 19 plus 15 is 24, 34 on day 3. For day 4, well, you've got 19 newly infected plants. So we just need to add 19. 34 plus 19, we'll add on 20, take away 1, 34, 44, 54, 53 on day 4, and then we can add on 23, which is going to add on 20, add on 3, 73, 76 on day 5, and if you really want, we could even have a day 6 where we add on 27, but you shouldn't really need it. Add on 20, 96, add on 7, 103, and that would be day 6. So what we need to do now is find an expression, and I'm looking at this. There is a constant second difference, plus 4, plus 4, plus 4. It's quadratic. I'm going to go straight to the regression tool and work this out. So, need to go menu and statistics. I now need to go back to n being 2, 3, 4, 5, 6. That's put the terms in, so that is 19, 34, 53, 76, and 103. Calc, regression, reg, and it's an x squared regression, it's quadratic. So that tells me it's 2x squared. 2x squared plus 5x plus 1, which means 2n squared plus 5n plus 1. And that is the end of the investigation paper.